let's start putting some more old stuff into our new stuff. The thing that we want to think of is integrating a region over, integrating a function over a region in the xy plane. So we could set this up as a double integral of a function of two variables, dA, where a is some little piece of a region. So we're going to imagine this region in the xy plane. And now we're going to define the boundary of the region as some curve C. And the orientation of the boundary is going to be such that the region is on the left as we travel around the curve. We want the region on the left as we travel around the curve. So that means we'll be traveling roughly, we kind of take a big view, we'll be traveling counterclockwise around the region. Now let's set up a vector field. I just talked about curves, so vector fields are probably going to show up because line integrals. So let's set up a vector field, and I'm going to say F1 is the I component of the vector field, and F2 is the J component of the vector field. Now we're defining this function. The scalar curl of F, the vector field, is the partial of F2 with respect to X minus the partial of F1 with respect to Y. So the Y direction stuff, dx, the X direction stuff, dy, and then subtract. That's called the scalar curl. I haven't justified why we would want to calculate this in any way. We're just setting things up to see what it tells us. An important thing to note is that the scalar curl of this vector field is a scalar function of two variables. Then I pointed out that when we're doing a double integral, we should have a scalar function of two variables to establish the height at any point above the region. So let's summarize the things that we've just set up. We've got a scalar function and a region. We can put those two things into a double integral. We've got a vector field and a curve. We could put those two things into a line integral. So now we should be very suspicious. I've got a scalar function and a region that we're going to stick into a double integral. I've got a vector field and a curve that we can put into a line integral. Anyone want to take a stab at what I'm going to be writing next? Scalar function plus a curve. I'm going to stick that into a line integral. Sorry, vector field and a curve that I can stick into a line integral. Scalar function of two variables and a region that we can put into a double integral. So I got a vector field and a curve C. I can combine this into a line integral. I've got a scalar function of two variables and a region. And we know that a scalar function of two variables can be integrated over a region, R, so we can have a double integral. So, anyone want to take a guess at what I'm going to write in between these two things? I'll give you a few seconds to think about it while I take a sip of my coffee to keep myself from talking. Set up a line integral, vector field F over a curve C. Set up a double integral, scalar function of two variables over a region R. The curve and the region are related. The vector field and the scalar function are related. If you guessed I was going to make these two things equal, you are absolutely correct. So what we have is that the line integral of the vector field dot dr will be equal to the double integral over the region of the scalar curl So once again, we integrate by looking at the boundary. That was one of the other ideas that we have floating through our work. We didn't have a lot of examples of this because it's just f at b minus f at a, or f at q minus f at p. But we're integrating by looking at the boundary. That's one way we can interpret what's going on here. And we've connected two very big ideas. The line integral of a vector field on a curve, and a double integral, where the vector field is related to the function that we're integrating, and the curve is related to the region. This is called Green's theorem. I'll write it in green. Little on the nose, don't you think? So Green's theorem says this line integral and this double integral will return the same values. So what do we need to do now, besides some examples and to point out some important conclusions to draw from this? We need to figure out what this scalar curl is telling us about the vector field. So that's something certainly that we should put on the agenda. So that's certainly an important thing we're going to have to deal with. What's the scalar curl tell us about the vector field? Other things that are still running. This is a new question that's come up because scalar curl is a new question. Other things that come up, what can we model with this dot product? What can we model with this dot product? So these are the two questions that we're going to have to deal with. Any questions? Excuse me. All right. Let's pause the video here and think about this for a little bit.